Hello everyone, welcome to Neural with Mohit. This series is going to be a rack series, and we are going to learn each and every important component of rack. We'll be starting with the embedding, right? And how does the embedding work? What exactly is the embedding? We will understand each and everything, and more on the as this channel is drive on. We will be discussing less on theory and we will be actually discussing more on hands-on, like how we can implement those so that it can the developers who are actually using these components and these features and who actually wants to use it in their day-to-day projects and all. So let's jump right in. So first, let's understand what is text embedding. And before we jump into text embedding, we need to understand that why text embedding is required and what exactly is text embedding, right? So what happens is when you give a sentence to, let's suppose any model, right? When I say model, I mean encoder, decoder model or any transformer model, any model, right? So when you give a sentence, like let's suppose an English sentence to the model, the thing is that the model does not understand text, right? So what it has to do is it has to convert that text to some integer, but it cannot be any random integer. That integer needs to have some, rules associated with it. Okay. So now let's understand that what exactly these rules are and what exactly is the need for this and what we are actually going to do in this particular case. Okay. So you must have heard that let's suppose the LLM has some context window, so that is the amount of information that model can actually keep with it, and then the LLM is able to you are asking it in some English language, some very general English language, and it is able to generate responses to you which are actually very much aligned to your query, right? Now, to do that particular thing, the model cannot work as we said, right? That it doesn't understand that text. So how will it work? So what happens is when you give it to a when you give a sentence to a to some model, what we do before that is that sentence is actually splitted in different tokens. Okay, now basically tokens are not exactly word, but to understand in a very layman understanding, you can consider like let's suppose each word is converted to a token, right? However, as I said, that token is not exactly a word. It can be a word, it can be, some delimiters in it, it can be anything over there, right? So it's not exactly splitted based on the spaces and all. Okay. But for the understanding sake, we are going to consider that token is a word. So what will happen is, first from the sentence, we will be extracting all the tokens. Okay. Now, once these tokens are extracted, these tokens are then converted to some integer value. Okay, now this is not going to be any random integer value. These integer values are defined in the model through a lot of learnings and all, right? So some numeric integer value is given to that particular token. Okay, now your sentence is actually, a series of numeric tokens, right? And then this particular thing is given to the encoder model. Okay, now why I'm saying the encoder model? Because the embeddings that you actually see are encoder model things, right? So the embedding that we are going to discuss, these are encoder model capabilities. Okay, so what we do is we give this token, the series of token to the encoder model, and what this encoder model does is for each token, it compares that token with each and every other token in the sentence, and then it tries to generate some understanding about that token. Okay. Now, that understanding about the token is actually the embedding that the model actually generates for you. Okay. So each token, what we do is we convert them to a vector embedding. Okay. Basically text embedding. We convert it to a vector basically, right? And these vectors are having some dimension. Okay. So what are these dimensions? These dimensions are nothing. So, dimensions, you can uh, understand how much of information that particular vector is storing about that particular token. Okay. So, like, let's suppose if we have to understand it in a very generic way, you can consider, like, let's suppose one of the dimension is pointing to the height. The other dimension might be pointing to the floor. Another dimension might be pointing to the shape of something. Another dimension might be, pointing whether it's an animal or human or kind of anything, right? So dimensions are nothing. These are the understanding about that particular token that you are receiving, right? And what happens is each vector, when we convert it to the embeddings, so these vectors are actually pointing to some direction. Okay, now that direction is actually in that, uh, like whatsoever is the vector dimension that you're seeing, based on that, the direction is defined. Okay, so like let's suppose if the dimensions are only two, right? In that case, the vector might be, pointing somewhere between x and the y coordinates, right? If the dimensions are three, in that case, the vector will be pointing somewhere between x, y, and z coordinate, correct? So in that sense only you understand that the vector will be formed through a lot of dimensions, and these dimensions are nothing. These are the semantic understanding of that particular token, right? Now, how does vector embedding helps us? Sorry, how does these embeddings help us? These embeddings are the semantic understanding of that token, right? As I said. So if there are similar embedding, what we say, vectors available, then those will fall a bit close to each other, right? And then you can actually create a cluster with those. So basically what happens is a similar meaning sentences or similar meaning words actually group together, and they give you the semantic understanding of that particular thing. Okay, so now let's understand this thing as we have written over here, that the AI model cannot directly process raw text. They must convert it to a numerical format. This process involves tokenization and embedding. So we have already discussed this, that the sentence that we are giving, it will be first, converted to tokens. So the text is first broken down into smaller units called tokens. It could be word, it could be subword, it could be character. We already discussed that, right? And we are generating these tokens using the tokenizers, right? Each is then assigned some unique numerical ID from the model's vocabulary. So as I said, these are not any random value. These values are assigned by the model, and these models actually go through a lot of training to understand that, what should be the value of that. Okay. Now, after the tokens are generated, these tokens are then passed to generate embeddings, right? So these numerical IDs are passed to the embedding model, where, sorry, which generates a vector of floating point number for each token, right? This vector is embedding and it captures the semantic meaning of that token. Tokens with similar meaning are positioned close together in high dimensional embedding space. So we have already discussed all these things. We understood this fact as well, that what these embedding helps in. These embedding helps us to capture the semantic meaning, and if there are similar kind of words which actually has same semantic meaning over there, so they will be falling close to each other, right? Now, what we will be now understanding and learning about these will be how we implement and how do we convert a particular, let's suppose, word to its embedding, right? So that is what we are going to understand, and that is what we are going to do. So we have some more theory written over here, like what we are going to use, so you can actually go through this and understand it more. Let us now jump into the implementation part of this. Okay. So, what we are going to do is first operation. So basically what I've done is I actually divided it into steps for you, right? So what you will be doing first of all is, first of all, you must be having some data source, right? From where you will be getting the data. So whenever we have a data source, there is, always one operation that we do, which is called extract, transform, and load. So extract means, you bring that data from whatever data source it is. In our case, today, it is going to be a PDF file, right? So we will extract the data from the PDF file. Then the second thing comes is transform it, right? So we actually transforms it to, any, like to our desired way that we want. Sometimes you want to remove some regular expression characters and all. So you do that thing over there. You do, sometimes you need to clean the data first before you load it. So you'll be doing the transformation of that, and then you will be loading that data for your model to use. Correct? So what we are going to do is we are going to use this PDF here. This is the PDF from Uber annual yearly report, right? And we will be using this particular PDF over here that you will be seeing, right? And this from this PDF, we will be extracting mainly text. We are not going to extract the images and all. So we will be extracting the text and we will be performing the embedding on the text for this particular exercise. Okay, so now let's come over here. I have imported few of the libraries and we will understand each and every library. So first one is the PyPDF, PDF reader. This library is actually used to read the PDF. However, I see one drawback in this particular library is that you cannot directly extract the tables from there, right? So for that, what I usually prefer is a pdfPlumber. So here you have a separate function for extracting tables and all, and you can actually do that. Right. Since if you're using Python, then you are, I believe, already aware of pandas and numpys. These are like, some of the highly used libraries in Python, right? And then we will be, as I said, that we are going to do embedding. So for to do the embedding, we will be needing some transformer models and we'll be using a sentence transformer from Hugging Face. And in that, we will pass whatever model we want to use. Okay. Then there is this UMAP implementation also. You can comment it out. I'm not using it. And then matplotlib. Anyways, we know that we use it for plotting the graphs and everything, right? So I've just segregated these things. And then there is one cosine similarity. So we will come to that. Once we come over there, we will understand that why are we going to use the cosine similarity. Okay. So as I said, for PDF, we have these two libraries that we can use, and we are going to use this one, the pdfPlumber. So how you use it is you first import the library, right? And after that, you will open the PDF that you want to open. And after opening the PDF, what I'm doing is I'm checking the length of the PDF, where I will be able to know that, how many pages are there. So let's do this. Oh, sorry. First, let's load all the libraries. So it will take some time for you, depending on, what is the capability of your system, and then it will. Okay. So now we can see that we have 142 pages in this. Let's come here and you can see here exactly 142 pages. So our PDF, sorry, our PDF load is successful here. Now let us move to the next part of this. So I'm using this, right? And you can see that, as I said, that pdfPlumber helps you extract both. It helps you extract text as well as the tables. So here is the code to extract table, right? So I will just run this code. So what we have done is we actually loaded all the complete PDF over here, and with the help of pages, we are able to traverse to each and every page, right? So what we are doing over here is we are traversing through all the pages, and in the page we are trying to extract the table content, right? Not every page will be having table. So definitely when the table is there, in that particular case, what we are doing, so as you see over here, if the table content is there, in that particular case, we are going to append it to a table setting. Right, so I'll just run this particular. It will take some time because you are reading through the complete PDF and then you are extracting the table part of that, and then you are loading the table part in this, right? So you can see in the sorry, on page 51, I'm able to see some table, right? So let's come over here. Let us try and see which page we are currently 47. 52, 51. Okay, so I think the page numbering is a bit different over there. Yeah, so I can see that we have a table over here. And to this particular thing also, I can see there is a table which says that October 1st, 2024 to October 31st, 2021. So let me just extract this. Okay. Yeah, so page number 47, and I can see that exactly this particular table is being loaded on this particular place, right? So we are having the table data over here. Okay. And after this, what we will be doing is we will be loading the text. Okay. For this particular exercise, what I will be doing is I will be mainly working with the text in this. And I will give you the assignment to work with the tables in this particular series, right? However, I've already shown you that how we can load the table and all, and you can see that it is loaded as an array kind of structure where you get all the columns over there and then the value for each columns, and you can actually convert it to a particular table format also if you want, right? So we'll be coming on this, and the same thing like how we did it for tables. Similarly, we are going to do it for like the text as well, right? What I'm doing is I'm also capturing the document name. So here, this particular code, what it does is it actually like splits it based on the forward slash, and then it takes the last item of that. And after taking the last item, I split it based on the dot, right? And what I do is I take everything before the last dot. So that will become my file name, right? So if I'll come over here, first I'm splitting based on this. So I will be picking this particular thing complete, right? And then after that, I'm splitting based on this dot, and I'm picking everything from 0 to one index before the last index, right? So I'll be able to pick it till here. Okay, so this will be my document name. And after this, what I'm doing are the same thing that I have done over there for the tables. We will be navigating through all the pages. From the pages, we will be extracting the text. So this page is the object that I'm taking from the pages, and this from page object, I'm extracting the text. Once the text is there, what I'm doing is I'm actually loading that particular text to my text content array, right? And in the text content array, along with the text, I'm storing few more information, just like what is the type of this. So type is text. Why I'm putting this over here is because here I'm using type as table. So when you are going to work with, let's suppose the multimodal embedding, in that case, you might need to keep a type for image as well, right? So that is how we are going to work. So I'm just preparing it from like from the beginning only to make it capable for doing any kind of embedding that I need, right? So I'll be keeping the type over here as well. Then the name of the document I'm keeping with me. Whatever page it is, I'm keeping the page over here, right? And then whatever the content of that particular page was, right? So what I'm doing is I'm going to run this particular thing as well. Okay, reader is not found because now we are using PDF reader, not the reader, right? So we will be running this with the PDF reader, and you can see that it was able to load everything, all the pages, because we have already, loaded the PDF much before, and then the pages and everything are already loaded. So here, what we are doing is we are extracting everything, we are putting it in each content, and we are checking this, right? So on page number one, it is saying that this is the text. Let us go here. Let us go to first page. On our way, 2024 annual report. On our way, backslash n 2024 annual report, right? So we have the exact same thing that we need. It is loading properly. The content and everything is coming as proper. Okay. So after this, what I'm doing is I'm converting this array of dictionary to a data frame, right? So what it will do is it will create a column name type, it will create a column name document, it will create a column name page, and it will create a column name content. As you've already, I'm assuming that you're already familiar with pandas, right? So like this is nothing new for you, I believe, right? So what we are going to do is we're going to load this thing, and you can see, as I said, that it has created all these columns, and in these columns we have all these values, right? And you can see that we have total 142 pages, and for each page we have these values. Okay. Now, after this, what I'm going to do is I am going to extract the value of document and page and type and actually put it in one column called metadata. So what I will be having, I will be having this metadata column which will contain all these things, right? So I'm going to do this over here, and you can see like my metadata is actually containing all these information, right? So this document contains the value of the document, the page will be containing the value of the page, and after this there will be a type as well, which will be containing the value of the type. Okay. So we have here, now if you see each row is having this value as a repeated value because I'm capturing it here also, and I'm capturing it in separate columns as well. So what I'm doing is I'm just reducing my number of columns I going forward, I will be, using only content and metadata. So you can see that in my data frame, now I have only content and metadata. Like this particular thing, I could have done it earlier as well over here itself, right? But then it would have been really difficult for you guys to understand that how I transformed it and made it to this. So we have already done the extract, transform, and load thing for our data. Now what we have to do is now we have to extract the embedding from the text contents, the text corpus that we are having, right? So for embedding, what we need is we need first of all a model that supports the embedding, right? And then we have to pass this particular content to that model so that it can do the embedding for that for us, right? Okay. Before we jump into that, let us also understand that what all different kinds of embeddings are available for us and which one are we going to implement. Okay. So, you might have heard of two, main embeddings because they are being used everywhere, which is like dense embedding and sparse embedding, right? So, first, let me explain you sparse embedding. So, what a sparse embedding is, it actually contains, let's suppose, the count of the word, right? It doesn't capture any semantic meaning. Let's suppose you have a very big corpus, and each corpus is actually each word. So you have a very big word corpus, and in that corpus, each word is actually an index of the array, right? And whenever in the sentence that particular word comes, so what you will be doing is you will be flipping that particular count to one, and rest all will remain zero. Okay, let's suppose your array is like this. So what will happen is you will be having a very high dimension array, but in that array, most of the values will be zero, right? And only very few will be ones over there. Like whatever word has occurred over there, only those are one, otherwise everything is zero. So you will not be able to get any factual understanding of that. You will not be able to get any semantic understanding of that. Correct. So that is the sparse embedding. It is actually not used for any similarity search. Like you cannot use it that great. So it doesn't perform that well in the semantic search because it lacks the semantic understanding capture capability, right? Now, what do we use for that? And like in our case, what are we going to use? We are going to use the dense embedding, right? So in dense embedding, what happens is each word, it will be, first of all, it will be a low dimension array, right? So it is not like each and every word which is there in corpus. For that, I should be having one index, one, index available for that, and I'll be flipping for that index. It is not like that. It actually captures the semantic understanding, and here the dimensions are actually relating to something. They are actually trying to capture some feature of that particular word, right? So that is how it will help you in the understanding of that particular word. So what we are going to use is we are going to use dense embedding. The one that we are going to do is also dense embedding, and here the dimensions are somewhere around 100 to 1024. Okay. After this, let's come to the quantized embedding. So here it is kind of dense embedding only, but we compress the bits over here. So you will be having fewer bits here, and with those fewer bits you will be having you'll be actually saving some memory, right? And it is very commonly used in FIRES. FIRES is a vector DB, right, that we actually use in RAG implementations and all, right? Then there is another binary embedding where the values will be either 0 or 1, and they are actually used for they are actually used to build the locality sensitive hashing algorithm for indexing. Right. And then there is multimodal embedding as well. Multimodal embedding are mainly, you use it for text and images. As I said that, like how we are loading the text and the tables over here, we can load images also, right? But we understood how the text can be represented in embedding, but how the images are represented in embedding. For this, what happens is there are special models who are trained on both image and text, and there, when you give them an image, they are able to understand the image, and they are able to, derive some valuable information from there. Okay. So for today, for this session, we are going to use All Mini LM L6 V2. It's a large model. Okay. And this is very good for text embedding. It has 384 dimension, And what we are going to do over here is from like first we are going to assign the model and then using the sentence transformers, we are going to load this model. Okay, so we'll be loading this embedding model over here. And after this, what I'm doing is from my text corpus, I'm picking up the content part, which is this particular column. I'll be picking that and I'll be converting it to a list and I'll be sending it to this model to encode. Now, when you do the encoding over here, as I said, right, so what we are doing is we are using a sentence transformer and these embeddings are generated by the encoder models, right? We discussed in the beginning itself. So what we are going to do is we are going to encode this value, and once we encode this, we will be having a semantic vectors over here, right? So let me just run this particular thing. So it will take some time because it is like going to, do all the embedding and everything. And let me do two things over here. Let me do this, and I will also print this for you. Okay. So let's see this. So you can see the dimension is 384 that we said. And now you see that what it actually captures. So here, as I said, right? So here it is like 384 values over here. And you can see all the values are non-zero values, right? So it will be having most non-zero values only. And it is a dense embedding where each and every value is actually trying to capture some feature about that particular word, right? So when you have a lot of words in this corpus, so what it will be doing is it will be trying to put those in the same cluster closer to each other basically, right? Here we are doing the sentence transformation, so each sentence like it will be picking it and it will be putting it in that same what we say group, right? And you will be able to identify those sentences very fast with the help of this. Okay. So till here, what we have done is we actually have created a set of embedding from our corpus. That was our goal number one. Now, what we will do with this embedding, right? So now let's come that where do we actually use this particular thing? Now, you must have, I believe most of you must have done this particular thing that you might be having a PDF. You take that PDF, you give it to ChatGPT, and then you start asking question to ChatGPT regarding the content in that PDF, right? So without even going through the PDF, you're able to ask ChatGPT in a very English-like language, and the ChatGPT is also able to respond you on that, right? So that particular thing that you see is actually the magic of embeddings, right? So here also what we have done is we were we have actually created the embedding out of this particular PDF, and now we are going to do the most interesting thing, the most interesting part of this session, which is like we are going to query on our embedding, and we are going to query in a very English-like language. We are not going to do a keyword search here. Rather, we are going to do a semantic search here, right? When I say semantic search, what it means is I am going to capture the meaning of that particular thing, the essence of that particular thing, and then I'm going to check that which of the information actually tries and help me on this particular thing, right? So this is the annual report, and what I'm doing is I'm asking it what is the Uber's revenue, right? Now let me just run this first. So what it will do is it will create a query. Now, as I said, that these models does not understand text. So what we need to do is we need to first convert it to an embedding, right? So we are converting it to an embedding, and you can notice over here I'm putting it inside the array block, right? Which means I'm using this as an array. Okay. And top K means what I'm going to do is I'm going to extract multiple results. So I will show you both the examples. There will be an example with the one result as well, and there will be an example with multiple results also. Okay. So let us do this. So I'm running this particular thing. I'm able to create the embedding for this particular thing. And now what I'm going to do is I'm going to do a cosine similarity search over here. Okay. So before we move further, let me explain you how cosine similarity works. Okay. So cosine similarity basically it checks. So when a word is converted to vectors, okay, and when you apply a cosine similarity on those vectors, so what it will do is it will check for the angle between those two vectors. So as I said, that each vector is actually pointing to some direction in the space, right? And when you bring another vector and you try and check the cosine angle for that, so you actually check that, in these two vectors, the direction that they are pointing to, what is the angle between these two? Okay. Now, if the angle between these two is zero, in that case, it means that they are exactly same. Okay. If the angle between these two is 90 degree, in that case, it means that, they are not related to each other. And if the angle between these two is like 180 degree, so in that case, what it means is that they are opposite to each other. Okay. So this is how the similarity search will be working. And the cosine similarity is actually executing over here. So what it is going to do is this query embedding, it is going to, we are going to do a similarity search on this, and this query embedding is now going to check with each and every sentence over here, and it is going to do a similarity search on those sentences and bring the similarity values over here. Okay, so basically, if I'll run this particular thing, right, and now if I'll say similarities, so I'm getting this one, right? Yeah, so I'm getting this as 142, right? So if you see this, what I am getting is 142. And how many sentences did I create it? I created 142 sentences, right? So what I am having over here is for each sentence, I must be having a similarity against those, right? So if I, let's suppose, say like, let's suppose similarity zero over here, right? And on this similarity I want to ask that, what is the value, right? So let's suppose I'll say what is the value of this zero. So it is going to say 0.15, right? If I'm going to say what is the distance between, sorry, what is the similarity between 0 and 1, so it is going to give you some number, 0 and 2, right? So with each sentence, if you see, I'm actually able to extract the similarities, right? So this is the same thing we are going to do over here. Now we have, I'll just keep it for you guys, right? So now we have the similarities over here that we have captured from this, and we can see that there are 142, which are exactly equal to the length of this embedding, right? Because we actually extracted 142 pages from our PDF, right? We extracted 142 pages from our PDF, and this similarities actually contains the similarity between each and every sentence. So this query embedding is actually, compared with each and every sentence, and you have the similarity score for each and every sentence over here. So first, what I'm going to do is uh, I'm going to first get the maximum what we say the maximum similarity. So what I'm going to do is I'm going to say numpy dot argmax, which will give me the maximum value from my similarities array, and this I will be putting over here, right? And this will be like an array, and I'll be getting the exact index from there. And then what I'm going to do is from my text corpus, I'm going to extract that particular index because the this has the maximum similarity, right? So I'm going to extract that particular index from my text corpus, and I'm going to print that particular thing. Okay, so let me just run this one. So what we have found is we found that 78, right? So the index 78 is the one which is having the highest similarity score, right? So now I will run it, and you can see that it has a similarity score of 694, which is close to 69% of similarity that it was able to get over here. And you can see that what was my query? My query was what is the revenue of Uber? Let me just do one thing. I actually have reduced this particular thing because we are capturing the full page, right? Let me just do, let me just print the first 1,000 words, right? So we are checking that query is what is the Uber's revenue, and it is saying that best matches at index 78 with this much of similarity score, and the content is that in millions expect shares amounts were reflected in this per amount year it is. this, and then you can see the revenue, and then there is some revenue given, then there is cost, and then all the cost and everything is given to you. And then at the end, it is telling you also that, okay, on this particular page, you can go, which is the metadata that we have captured, right? So we are actually printing the metadata as well. It is saying that go on this particular page, and there you will be able to see this particular information, right? Please note that I have only printed the first 1,000 characters. If you remove this particular thing, then you will be able to see the complete content, which will be even much more bigger than this, and you will be able to see all the content, right? I did this so that you will be able to see, some get some sense of this. Otherwise, the content will become too large. Okay. Now here, what I did is I actually got the maximum item, right? Which is just one index, correct? So I said that which one is having the maximum similarity, give me that. But generally, when we are working on RAG and all, so what we do is we actually get two or three, results that we feed to our large language model to generate results. Okay, so I said that top k, the value of k, top k was 3. That is here. The value of top k is 3, right? So what we are doing is I'm saying that sort these similarities, okay? And then after sorting, do this, get the top three from there. And those top three indices, what we will be doing is we will be going to a text corpus, which is the text doc, and from there I'm extracting the content and the metadata, and then I'm printing those. Okay, so now let's do this as well. So you can see, let me just do one more thing. Let me make it 1,000 so that you will be able to see some values over here. Okay, so as we have seen, the highest was this one, right, with the similarity score of 69. It's the same page, 78 page. This we have already seen. Then after this, there is this on index 97, page number 98, basically, where you can see the score is 65, and it is also talking about the revenue. Like you can see that the note 2 revenue, the following tables and all, and then it is also discussing about the revenue in mobile, delivery, freight revenue, and everything, right? And the total revenue then, right? And if you see after this, I am searching, like what I'm getting is the index 83, page number 84, and it is having a similarity score of 64, right? And here also, if you will notice, it is also talking about the same kind of thing where it is talking about the net income and everything, and then it is giving you the result, right? So this is how the cosine similarity works. So as I said, that what it does is it checks the direction between the two words, and then using that direction, it actually tries and build a semantic relationship between those. So as you notice, right, like you all must have used RDBMS and all in in your work and all. And what you notice over there is there we do the exact keyword search, right? But here what you are doing is you are actually trying to extract the meaning rather than the keyword. So here, after giving the PDF, what I just said is tell me about the revenue, and I'm able to extract those pages where the revenue of Uber is actually defined, right? So this is how the cosine similarity here works. Uh, Along with cosine similarity, there is another way to do a semantic search, which is called the dot products. Okay, we'll discuss both. Cosine similarity already we have already discussed. Now we are going to discuss the dot product, and then we'll understand both, like when to use what. Okay. So as I said, cosine similarity mainly considers only the direction, and most of the models that you're going to use are trained on this, right? So this is like one of the thing which is more popular, which is more in use when you will be doing. So cosine similarity is something which actually helps you understand that thing, right? Now let's come to the dot product. Now, what is dot product? It is also kind of the same thing, but here there is one more thing added, which is the magnitude. Okay, so some models are trained in a way where higher the relevance, more will be the magnitude of that particular vector, right? Lower the relevance, lesser will be the magnitude. And as I said that, we choose the embedding based on what model we are going to use, right? So if your model is trained on this particular thing, means if the model is trained on dot product, right? In that case only you should be using the dot product in your searching. However, what I feel is like when you see this, and if your model is trained on that, then the results over here are much better, right? But yeah, as we did the embedding, and here we are going to do the same thing using the dot product as well. So what it does is some models are trained to generate higher magnitude for more relevant text that we have already discussed, considers both magnitude and direction of the vector that we have already discussed, and use only for models trained on dot product, right? So all these three items we have already discussed. So now, how does this dot product work? So this is nothing. This is the matrix multiplication, right? So if I'll give you in that layman term, it's a matrix multiplication, and the rule of matrix multiplication you all know, right? What is the rule? The rule is like the number of columns over here should match the number of rows over here, right? So that is what we are doing. So to do that particular thing, what we are doing is we are transposing our embeddings array. Okay, so here we will get the matrix similarity score, dot multiplication similarity score. From that similarity score, what I'm going to do is the same thing that I did over there. I'll be sorting it and then extracting the first three items. Okay. And after I am done over there, what I will be doing is I will be printing these values, right? So let us do the same thing. And let me also increase this value so that we'll be able to get some more data over here. Okay. Now let's see. We will, so what we saw in the cosine similarity, the first was the index 78 with this score, and here also we are seeing the same thing, right? Exactly same result we are getting here. Second is 98, exactly same result. And third was 84. 84 is here. Let me also see which one is here. Yeah, exactly 84 is here, right? And the score is 6435. 6435, right? So what you can see is with both these, we are actually able to get the exact same score. We are able to get the exact, same pages. But where the difference lies is the difference lies over here, right? So if your model is trained on dot product, this is going to perform much better. If your model is trained on cosine similarity, then this is going to perform much better. Okay. So yeah, so if you've noticed that we are able to ask questions from our PDF without even going through it, right? So now you know that which all pages are required. Like let's suppose you get some, so I'll tell you where can we actually use it, right? So let's suppose you get some text documentation, and in programming we have to go through the documentation, especially if the software is, let's suppose, built by someone else, right? So what we do is we go to the documentation of that software and that API and anything, right? And these documents are really overwhelming, right? And you know that exactly what you're going to search for exactly. So in that particular case, what you can do is you can take that document, load it in your embedding model, and then simply ask the questions that you need from that document, right? And you will be able to like increase your productivity very high. And now you actually need not have to give it to ChatGPT also, right? You can do it yourself. So after you learn this particular thing, what you can do is you can actually load the document and start asking question to it, right? Okay, so if you're till here, embedding is already done. Now, what we are going to do is, as I said, that it captures a semantic meaning and it clusters and everything, right? So now, what I'm going to do is, I am going to work and show you on the visualization part of the same, right? If you want to drop, you can actually drop here and start implementing it, because after this particular thing, this actually you're not going to use in your work. To be honest, this is for your understanding that how the embedding is actually placed in the outer space, right? Sorry, in the vector space. Okay, so let me just run this particular thing. So what I'm doing is I'm getting the PCA, and why I'm getting this PCA, I'm going to do the dimensionality reduction. So you notice that there I was having 384, and I'm going to reduce that to 2. Now, how does it work is it will try and keep merging each and every dimension, capturing the semantic meaning, and then at the end it is going to like each dimension is going to like capturing multiple features in it, right? So what happens is you actually lose a lot of things over here. But overall, like, if you want to visually represent it somewhere, the two-dimensional space is what we basically use, right? Or the three-dimensional space is what we can use. More than that is like it becomes really difficult for us to even understand. Okay, so let us run this. Cool. So I did that, then I did the k-mean, and I'm creating the clusters. Okay, so what I'm saying is I'm saying I want three clusters over here. So basically, wherever the points will be scattered, those will be formed in three major groups. Okay, now let us see what I'm. So here I'm getting all the labels of that, and I'm saying that how many labels do I have? So my cluster 0 has 82 sentences, my cluster 1 has 31 sentences, and my cluster 2 has 29 sentences. Okay. And this particular code, what it is doing is it is actually just creating a graph for you, and it is going to represent you that same thing over here. Right. So see. Okay, and here what you can do is I must have commented a code, which is like yeah. So here what you can do is in this embedding, you can actually say dot apply and send the wrap text. So call the wrap text over here. And what it will do is it will actually break it in lines as well. So right now you can see that these are like overflowing on this graph. But yeah, so basically you can see that there are three main clusters being formed. One is blue, one is red, and the one is yellow. And each cluster will be having some the sentences that you will see in those clusters will be related to each other much closely, right? So this is all about embedding. We discussed text embedding today, and what I want you to do, right? So which could be yeah, so which is going to be a homework for you. What you need to do is you need to actually uh, so I have done it only for the text, right? So what you need to do is you need to do the same thing for tables as well, right? So I've already put it over here. Metadata and everything is here. What you just need to do is you need to capture the table as well, and you need to get all the table values in that. And when you are doing a search, you need to get the table results as well in your search. Okay, cool. Let's meet in the next video. As I said, that this is going to be a rack series. So what we are going to do is so we already learned text embedding. Now the next that we are going to learn is vector databases is what we will learn next. Okay, so if you have liked this video, I would ask you to like it, share it with your friends so that they can also learn about text encoding, so text embedding, right? And please subscribe to the channel so that you will be notified whenever I upload a new content. Thank you.